Welcome to my 3MT video. What do environmental monitoring, autonomous driving, wireless communications and smart buildings have in common? The answer is, all these interesting research fields rely, in one way or the other, on knowledge about underlying physical phenomena that vary as a function of location, or as I like to call them, spatial signals. A key challenge is often the identification of areas where spatial signals behave somehow differently from a well-defined baseline state. A self-driving vehicle, for instance, should be aware of streets with lacking wireless coverage to avoid losing signal while driving. My PhD research is concerned with the development of statistical signal processing algorithms to precisely localize areas of anomalous signal behavior based on information gathered by large-scale wireless sensor networks. These consist of hundreds or thousands of battery-powered nodes, so efficient usage of the already congested wireless spectrum and a long sensor battery lifetime are essential. Let me illustrate the central idea behind the methods developed during my PhD. First, discretize the observation area by a fine spatial grid. Per grid point, define a binary state of the spatial signal. Is everything going as expected? Then the so-called null hypothesis H0 is in place. Is something unusual happening? Then the alternative H1 holds. To achieve a good spatial resolution, the number of grid points is large, hence many simultaneous binary decisions are made, which makes this a multiple hypothesis testing problem. But how and why does solving this multiple hypothesis testing problem efficiently provide meaningful estimates of the area where the signal behaves anomalously? Well, each time an individual node uses its transmitter, battery power and wireless bandwidth are being consumed. Hence, in my methods, a node turns on its transmitter only once to send a few bits. This is possible because each sensor condenses its local measurements into a single scalar summary statistic that quantifies the local support for H0. In the cloud, the empirical base probability of H0 is computed for each sensor location and interpolated in between sensors. The area of anomalous signal behavior is then inferred from these probabilities. The methods from my PhD research learn all required statistical models autonomously from the data and fulfill statistical performance guarantees in terms of the false discovery rate. On average, no more than a predefined limit, say 10% of the estimated region of anomalous behavior, are false positive, so grid points where the signal actually behaves normally. This makes the estimates trustworthy and useful. In cognitive radio, for instance, you want to be able to control the probability that a secondary user accidentally accesses a primary user's frequency band. I hope that my work serves as a foundation for the development of a wide range of innovative products and services that require the real-time monitoring and analysis of spatial signals. Thank you for watching.